Of what astronomers call the puffy hot Jupiter problem, because we don't know how you can get a planet this big, and this puffy is a very puffy planet, that close to its sun. We don't know how it formed there. We think it must have formed out here, and it must have migrated like that over millions and billions of years. The other thing that's really interesting is I said it was the styrofoam planet. I said it was a puffy planet. That refers to the fact that K7b here is very, very underdense. It's not dense at all. It's very big, it's very light. And in fact, it's so light, it's lighter than styrofoam, and it will float on water if you could put it in a giant bar. So K7b is a very popular destination. It is a gas giant planet, which means you won't be standing on the surface. But if you're interested in taking a visit to a planet where you can actually stand on the surface, I can recommend on the posters behind you here, HD 4007G. It is what is called a super Earth planet, which means it's only a couple of times the size of the Earth. And we believe it is a rocky planet because we have a measurement of its mass and of its radius and size, and so we think we can figure out what it's made of. We think it's made of rocks and ice mostly. Well, HD 40307G being twice the size of the Earth does have 8 times the Earth's gravity, so unfortunately you couldn't stand on the surface without being crushed. It is very popular, however, with adventure sports customers and those who like to do a little bit of weightlifting. So these planets that start with Kepler have been discovered by the Kepler Space Telescope. It's a wonderful telescope just sitting out there, so I'll show you a picture of it. There's Kepler, that's what it looks like. And that's the direction it's looking in. All of these planets have been discovered by Kepler. There's that little patch on the sky where Kepler has been looking. And Kepler has discovered thousands and thousands of planets. Well, hundreds and hundreds of planets that we've confirmed and thousands that we know are potential planets. And so we've been looking there since about 2008. Unfortunately, Kepler broke down recently. It's no longer staring at the same patch of sky. It's now kind of drifting semi-aimlessly across the sky. But it can still be used for science. There's been some very clever rejigging of the way it observes done. So does anyone have a particular planet they'd like to look at? Otherwise I can invite you to peruse our brochures, which will let you know about some of our more popular locations. And I hope you'll consider the Exoplanet Travel Bureau for your future travel needs. Oh, actually one
We've got a name called Odyssey. When you look at the stars, loads of light. So you can see it. So you can see So that's the kind of stuff that we do. So in our research group, we are looking at these black holes, and we're looking at the light that's coming from around the black hole. But they're actually really, really small regions. So when we look at it with a telescope, it just looks like a point. We just see light. It looks like as if it was a star. But it's not a star. It's the material around the black hole. And so what we do is we try. So the information that we have from the regions around this black hole is we know the energy of the light, and we know the arrival time of the light particles as they hit our detector. And so from these two things, the energy and the time, we try and reconstruct a picture like this of what it must look like. And what we're actually finding is really cool, is that the light that is emitted here from the close side of the black hole is arriving before the light that comes from here. And that's a really crazy thing if you think about the distances. We're looking at these black holes that are 100 million light years away. So the light from this black hole was emitted 100 million million years ago. And yet we can see time delays between light that is emitted here and here. And the time delay is like 30 seconds or something like that, really small, even though it's really far away. So that's how we can use the timing information to kind of tell us, reconstruct a picture of what we think it looks like. And that's part of the work that we do here.
Biscuits make you fat. Let's eat chocolate biscuits. My wife knows all about chocolate biscuits.
Did you hear that? He said she said his favourite biscuit was chocolate biscuit. So how do you eat a biscuit? I know you've got to ask, I don't know.
How do you eat a biscuit? Very slowly.
Type stuff. So I think there's room for failure as well. It's not that you get.
Oh, it's not always that it turns out.
No. I mean, what I get, just one of what gets just thrown away.
Okay.
So you might get 3 failures for one good piece. And each piece is unique as well. You never get you never get another one the same. You might get something similar, but you won't get it the same.
You have made all these yourself?
No, I'm the astronomer that's worked with. We're working. Well, my group is working with a group in Cancer Research UK. So we're doing some scientific research together.
Right.
But Libby Fink is the artist, and she. Well, I use that word, inspired, with the idea of showing some way of representing the similarities between some of the things that are very small, such as cells, and the stars. Sort of, my main work is with star structure in our galaxy, but the work we're doing with the oncologists and cancer researchers is more to do with looking at the imagery and getting the most information out of those images fastest way and these sort of things. So,
So you're doing that the same thing with space as well.
So we're the same. The sort of
and
techniques we're using with just analysing our star images. We can also use for analysing their cell images, and that's quite handy. So it's it's nice to see some artwork that's sort of come out of this as well.
Exactly, it's beautiful.
And
it's lovely.
some of the images that we provided to Libby, so some of that galaxy, well, it's representative. It's very similar to a galaxy picture which is on the wall outside. You'll see, and there it will be. That sort of type of galaxy is called a shell galaxy, and then you might see the little pinpricks of light and stars around. And there's another one over there which is quite representative, the little one, quite representative of how a star might appear with little planets going in front of it. And you'll see when it's fluorescing, it just looks like a planet. But when you see the white light, you see some little specks, which will be like what the planets will be going in front of the star. So it's quite, it's quite neat to see that.
Very unique. It's beautiful. I mean, it's beautiful to look at just like that, and then when there's the meaning behind it, it's kind of with it.
Yeah. So it's nice stuff to have.
Thank you. It's very
And so by using this kind of things to describe these two components, we can construct some kind of models to describe our universe. And in fact, this model fits with our data theory experiments by creating particles and try to make them collide. And in this kind of process, you might have some chance of creating new kinds of particles. And these kind of new particles may be some candidates for the dark matter. And so that's why we hope to look for the dark matter in this kind of experiments.
Do you think that, say, many years down the line, we could, say, use dark matter and dark energy as maybe a suitable fuel source, or is it more of an external body which we can't control?
Not quite understanding your...
Oh, so say dark matter and dark energy is, say, many years down the line where we have a greater understanding of it, do you think we could use it practically in our everyday lives, or is it more of an understanding as to how the world functions?
Well, yeah, that's some interesting thing I've never thought of. But, well, at the moment, of course, like perhaps we may discover some kind of new theories to explain our universe. But I mean, on Earth, we hardly notice any difference with or without dark matter, dark energy. But like, of course, scientifically, it might drive into a new direction that we might propose some new theory to explain our universe. In that way, I think it's useful.
Why is it assumed that dark matter is in particle form?
Sorry, can you speed up a bit?
Why is it assumed that dark matter is in particle form?
Ah, right. So the question is, why do we assume dark matter is a particle? So basically, we may treat dark matter as something that would interact gravitationally. So, and then according to our knowledge in physics, basically all kinds of particles would interact gravitationally. So that's why it's a natural consequence of assuming that this is a